Power relations in AC circuits. In the previous class, we have derived the equation for the average power, that is PVA equals to VI cos phi, where the term cos phi is the cosine of the angle between the voltage and current is known as the power factor. The power factor, which is cos phi, is equals to unity 1 when phi equals to 0 degrees. This is in case of purely a resistive circuit. In inductive circuit, as phi value equals to minus 90 degrees, it's lagging power factor. In case of capacitive circuit, phi equals to 90 degrees plus, so it is leading power factor. In case of inductive circuit, I leads voltage. Here I lags voltage. Now apparent power. The product of VI is called apparent power and usually indicated with the symbol S, and it is expressed in volt amps. Reactive power. The product of RMS values of voltage and current with the sign of the angle between them is called reactive power in AC circuit, and it is denoted by the letter Q, VI sin phi. This power is also known as wattless power or quadrature power. P equals to VI cos phi, which equals to V, we can represent with IZ, where Z is the impedance, multiplied by I, and cos phi is nothing but R by Z, which equals to I square R. Similarly, quadrature power Q or wattless power or reactive power Q is given by VI sin phi, that is I, Z is the voltage and I is the current, and sin phi represent with the reactance by the impedance. Then we are going to get I square of the X. X is the reactance. We can observe from these two equations that P is always positive for any value of V and I until the angle is between 0 and 90. Thus, even if V and I are AC quantities, P, that is the real power in RL and RC circuits, is always positive. And it is also true that I square R is the power loss in the resistor, and for any value of I, the magnitude of I square R must be positive. Q may be a positive value or a negative value, whether X is positive or negative. For an inductor circuit, X is equivalent to JXL. For a capacitive circuit, X equivalent to minus JXC. The reactive power Q for inductance is a positive, while the capacitance is a negative. For pure inductance and a capacitance, that phi equals to 90 degrees plus or minus, where P equals to 0. Thus, the pure inductance or pure capacitance does not consume any real power. In inductance, the reactive power is consumed to develop the flux, while in the capacitance, the reactive power is function is to store the energy. Now, the total power S is the vector sum of P and Q. Now we can know that the power factor is cos phi, which is given by R by Z, or cos phi equals to the real power divided by the apparent power, which equals to VI cos phi by VI. Then watts, real power divided by volt amps. Now the sign of the angle between V and I is given by the reactance divided by the impedance, which equals to Q by S, that equals to VI sin phi by VI. This can be measured in volt ampere ratings divided by volt amps, and this is known as reactive factor. With the reduction of the magnitude of phi, the phase angle between the voltage and the current, the power factor but cos phi increases, whereas the reactive factor, the sin phi, decreases. To improve the power factor in any AC system is highly desired. Now, for pure resistive load, phi value is 0, power factor cos phi equals to 1, that is unity power factor. The real power PVI cos phi is 1, so P equals to VI. The Q value equals to VI cos 0, which is nothing but 0, so 0. Then The apparent power S is given by square root of P square plus Q square. Now substitute this, then you are going to get Vi. For pure inductive load, phi equals to minus 90 degrees, then cos phi equals to 0. As a negative sign is there, 0 lagging power factor, then P is given by 0 and Q is given by Vi as the sine of 90 degrees is 1. The apparent power S is given by same formula, that is P square plus Q square, which is equals to the total power Vi. For pure capacitance, phi equals to 90 degrees, cos phi equals to 0, then 0, this is positive, so leading power factor. Then P is equals to 0. If you substitute, then Q equals to Vi. Then the apparent power S equals to square root of P square plus Q square, which equals to Vi again. Now for RL load, phi value will be between 0 and 90 degrees. Lagging again, P is given by Vi cos phi and Q is given by Vi sin pi. The apparent power S is given by, if you substitute these values of P and Q, you are going to get Vi. RC circuit loads, then the angle between the V and I is in between 0 and 90 degrees, but this is the leading. Then P is given by Vi cos pi, Q is given by Vi sin pi, then S is given by Vi. This is the tabular form representing different expressions of power and power factor for different loads of AC circuits. Next, power triangles. It is a geometrical representation of apparent power, average power, and the reactive power. In an inductive circuit, the current I lags the voltage by an angle phi, which is a negative value. Construct a rectangle triangle. Then this is I sin phi, and this is I cos phi. In terms of power, Vi cos phi, which is going to give us the value of P, and Vi sin pi, which is going to give us the value of Q. This is the vector sum of P and Q, Vi, that equals to the apparent power S in case of inductive loads. In case of capacitive loads, the voltage V, then the current leads the voltage by a angle phi, which is a positive. This is nothing but I sin pi, and this is nothing but I cos phi. This is Vi cos phi, which is nothing but a value of P. This is Vi sin pi, which is nothing but the value of Q. Then the apparent power S is given by Vi, which equals to the P plus Q vector sum of the real power and reactive power. In case of a capacitive, these are known as the power triangles. Let us see what is complex power. The three sides of the power triangle, as we already seen, that S, P and Q, all we can obtain from the value of V and conjugate. The product of Vi is known as the complex power. Now let V equals to V E J theta. Then I equals to I E J of theta plus phi. Then Vi conjugate complex power is given by V e to the power of j theta multiplied by I e to the power of j theta plus phi. That equals to Vi e to the power of j of theta, as this is a conjugate, minus. So minus theta minus phi. Theta theta gets cancelled, then you will be getting Vi e to the power of minus j phi. This you can elaborate and write that Vi cos phi minus j Vi sin phi is nothing but the complex power. This complex power can be represented with the letter S, apparent power, and Vi cos phi is P minus j of Vi sin phi is nothing but a Q. As we got the negative reactive power, this is in case of a capacitive circuit. In case of inductive circuit, as the phi is negative, we will be getting Vi conjugate is equals to V e to the power of j theta I e to the power of minus j of theta minus phi. Now we'll be getting Vi e to the power of j of theta minus theta plus phi. That is Vi e to the power of j phi. That equals to Vi cos phi plus j of Vi sin phi. Then the complex power S equals to P plus j cube. As the reactive power is positive, it is representing the inductive circuit. Positive indicates lagging reactive power and negative indicates leading reactive power. For capacitive circuit, reactive power is negative. For inductive circuit, reactive power is positive. Here, the reactive power is useful to store the energy. Here, the reactive power is going to develop the flux. Let us solve one problem. Apply the node analysis at node X and assume the voltage at the node X. This is a node X you can represent at anywhere. The voltage is V. Now, you are going to get the current at node X from this branch V by 5 plus V by from this branch J 2 ohms plus V by the total impedance is 2 minus J 10 is given by this is the current coming to the node 1 at an angle 0 degrees. Or we can represent this 1 plus j 0. Now solve this and we will be getting V by 5 minus j 2V by 4 plus V 2 plus j10 divided by 4 plus 10 square which equals to 1. Then V by 5 minus j V by 2 plus V by 52 plus j 5V by 52 equals to 1. Now solving this, we'll be getting real and imaginary terms 0.2192 minus j 0.404 volts equals to 1, from which V equals to 1 divided by 0.212 minus j 0.404. Going to get 2176 at an angle of minus 61.52 volts. Now the magnitude of V is nothing but 2.176. And the angle between V and I, phi, equals to 61.52 degrees. The active power P is given by Vi cos phi. That is 2.176 multiplied by the current I is 1 and cos of the angle 61.52. It may be a negative value. Cos of negative is again a positive value. Then you are going to get the real power, that is 1.04 watts. Now, the reactive power Q is given by Vi sin pi. That is 2.176 multiplied by 1 multiplied by sine of 61.52 degrees. Then you are going to get 1.913 VAR. Now, the total power or apparent power S is given by square root of 1.04 square plus 1.913 square. You will be getting 2.177 VA. Now we can find out the real power dissipated in that P 5 volts or losses. We can write this I at 5 volts square of the 5 ohms. I at 5 volts is V by 5. V by 5 whole square multiplied by 5 ohms. Substitute the value of V from here. Then if you calculate this, you are going to get 0.947 watts. Similarly, power dissipated in 2 ohms given by the current at this branch, that is V by 2 minus J10 whole square multiplied by the 2 ohms. If you calculate this, you are going to get 0.09 watts. This is the real powers dissipated in the resistors or power loss in this resistors. If this video is useful, please like, share and subscribe.